So first and foremost, you should type in your attendance. All right. Hopefully you can see the screen. Okay. So first of all, let me clarify a couple of things here. Before starting the class, perhaps I should have told you about some of the prerequisites that I will need uh, for you so that you can follow the course content properly. So here, let me write prerequisite that you should. I mean, these are not very something major. You should already have some elementary idea about these things that I'm going to mention. Okay. So first of all, and on the calculus side, you should have a very good grasp on the partial derivatives and so on. So you should understand what are partial derivatives. Okay. Uh, and multivariable calculus. Okay. And then you should understand differential equation. Someone's mic is probably on. Can you please turn it off? So then differential equation. And their solutions, mostly second order differential equations, and to some extent tensor calculus. Okay, so tensors, this should be taught in your mathematical methods course. I don't know what is the course code for that. I guess PH 651 or something like that. Okay. So pay particular attention to this part, and towards the end of this thing, we would be using tensors here also. We would be using notations that are compact there. Now, for the physics side, you should understand what are constraints of motion. So this would have been part of your undergraduate course, but if you do not know it, these are not anything major. You can ask your friends. So constraints and the types of constraints also. Okay. Like holonomic, non-holonomic, scaleronomic constraints, and also. And then generalized coordinates. Okay. So what are generalized coordinates? Okay. So in the beginning of any classical mechanics textbook that deals with Lagrangian and Hamiltonian, you will find this in these topics. Okay. So make sure that you understand these quite well. Okay. Otherwise, there would be problem in following the things that I am going to be talking about here. Okay. So I should have mentioned this perhaps in the first class, but it escaped my mind. Uh, Now that is out of the way, what we can do, there are a couple of more instructions. So perhaps you have noticed that in the Google Classroom page, you can see a new topic called homework. And I already told you that from time to time, I would be uploading homeworks there. And some of you have already started to submit your homework, which is good. And so to keep things organized, okay, perhaps now by now you have understood that if you send me an email, then it is very difficult to keep everything in the same place. So that's why I created this Google Classroom, so that everything related to PH 603, the classical mechanics course, are contained in there. So to make things organized further, when you submit any PDF in that homework section or mid-semester as an answer to mid-semester or quiz or something like that, you should follow a naming convention for the PDF. Okay, so let me so naming convention. Oops. So the naming convention you should follow is that it should be your name, hyphen surname. If you do not use a surname, that's fine, skip this part. Then your roll number. Okay, 21. And then what is the thing that you're submitting? If it is a homework, then just say HW number 1, number 2, or whatever. So what, homework 2, and then .pdf. Okay. And if it is a mid semester, then write mid sem, something like that. So, but this should precede those things like name hyphen surname, or if you do not use a surname, just name hyphen your roll number. So 2103 blah blah blah, then hyphen homework 3 dot pdf, something like that. Make sure you name your PDFs in this way. Okay, so that it's easier for me to find out who is whom, which. And for those who have already submitted for this homework one, you do not need to do anything. But from now on, keep this in mind. Okay? Whenever you are naming your file, uh, name your PDF file in following this particular format. And there are no spaces in between. So name hyphen, there is no space anywhere. Okay. So the hyphen plays a role of space. Okay. There is naming convention out of the way. And now I have again one request to you. So I need a list of people who are attending the courses. So I noticed that there is one student who have not joined the classroom yet. So his name is Kapil Mehta. Sometimes I think it's Kapil Mehta. So does anyone know this person or has any contact with this person? I do not know what is happening with this person, but he or she is not attending the class. I don't know if he is checking the email or so. So if anyone knows this person, please let this person know that the classes are already on, and if you do not join quickly, you might miss something. Okay. And another thing I will need is one Excel file, like a list of containing the list of you who are attending this thing. So basically, in column 1, you just put the serial number, and then column 2, you just put the roll number sequentially here. And then in column 3, you just put the name of the student, like your name. Okay. And so you prepare the Excel file of the people who are attending this course. I think it's 26 rows will be there because of this, and send this Excel file to me. So can anyone volunteer to do this and send this to me?
But actually, we don't know about the people, the students who are not attending. Actually, some days, like someone is coming, then there is a gap.
Yeah, but perhaps you can see the names in Google Classroom, right? Everyone who is at least joined.
Okay, so according to that, so
Yeah,
the
you
Excel
can
file is
just.
already available actually.
Sir, I will do that.
Okay, so any one of you just compile it and send it to me.
Okay, sir.
Okay.
Sir, in your
Okay.
email or in the classroom?
In my email. So send this in my email. Okay. So for this, just email me. And yes, that would be necessary. So according to my information, 26 people have registered for this course, and among 26, only 25 are attending. Like according to Google Classroom, 25 students have accepted the thing. Okay. So then yeah. Okay, so that's it then. Now we can continue to the main part of the lecture. Okay. So any confusion regarding this? Okay, good. Done then. So now, again, back to the Lagrangian. Okay. So we have found out that if L is a function of only one q, so L is just a function of qt, q dot t and t. Then my Euler-Lagrange equation for this is very simple. Sorry, d dt of del L del q dot minus del L del q equals 0. So it is, there is a comment. So due to network issue, I am not able to understand your words clearly. Oh, is that a problem for everyone, or maybe his network is?
No, sir, you are clear.
Okay. Okay then. Shankar, do not worry. If you cannot hear me right now, just try to hang in there, and later you will see the recording. Not a problem. Just try your best. Not an issue. All right. So now the straightforward generalization would be, suppose you have n such q's. That means you have say q1t, q2t, blah blah blah, up to say qnt. So n number of q's, okay, which I will concisely write as qkt with k running from 1 to n. Okay. Then the Lagrangian would be a function of all these q's, so qkt and qk dot t. When you see this, you assume that k is implicitly running from 1 to n. Okay. Now you can play the same game. So basically, the two-dimensional plot I draw for q and t, that would be a multi-dimensional plot, and you have to find out the correct path in this multi-dimensional plot. So the kth coordinate you might parameterize as so qkt you might parameterize as the correct version of this 0th path. So you call it qk0t plus some alpha times some eta kt. Okay. So this eta k is again an arbitrary function of t. Now again, if you play your cards right and you apply it to your variational principle, you will find for the kth coordinate for so for qk, the Euler-Lagrange equation will be of the form, at the page here, will be of the form d dt of del L del qk dot minus del L del qk equals 0. Okay, and there would be k such equations. Sorry, there will be n such equations. So these would be valid for k equals 1 up to n. So there would be n number of Euler-Lagrange equation, and this is the equation for qk. Okay, so this is one particular equation for qk, and there are more such equations, and there are n number of equations. This is a straightforward generalization. I hope you can figure it out. Now the question becomes, how will we use this formalism in a physics problem? Okay. And this is where I would try to present a new point of view from perhaps what you are familiar with. Okay. Now, perhaps what you have seen in your undergraduate days is this. Suppose you are given equation of motion. By equation of motion, I mean that you know the force law, the law force that that the system is governed by, and from that equation of motion you construct a Lagrangian, and then cross verify that that equation of motion is actually indeed the equation of motion that is that you obtain from the Lagrangian. Now, if you think in this way, so if you know the equation of motion already, suppose I know the Newton's second law of motion, okay, and now you write L equals T minus V, Newton's second law, and you get back Newton's second law of motion. But the thing is that this point of view seems to be quite useless, because if I already know Newton's second law of motion, okay, I can solve all the problems with that. So why do I need the Lagrangian formalism at all? Okay, so my ultimate goal for a dynamical system is to find the equation of motion. If I already know the equation of motion, then there is no point going back to the Lagrangian. Why do I need the Lagrangian for? What additional insights does Lagrangian give me? When it does give you something, some mathematical sophistication, but it's just that. It's just a mathematical sophistication. Why would I need that if I already know the equation of motion? So the point I'm trying to make is that Lagrangian formalism, or this abstract formalism of additional principle, is not the most useful principle when you already know the equation of motion. It's the most useful when you do not know something. Okay, and so our goal for this part would be that you take the known set of examples, things that you know, like Newton's second law, let's say electrodynamics, and try to find a Lagrangian formalism for them. And by doing that exercise, you try to extract some general principle that transcends beyond that particular example of electrodynamics or Newton's second law, that is more general. And then you start to believe on those general principles instead of a Lagrangian principle or the equation of motion themselves. So you then basically hypothesize that those general principles are the principle of nature. Nature obeys those general principles. Okay, so I'll be trying to giving you the flavors of what I mean by this thing. So to begin with, uh, let us let us take the example of a free particle in one dimension. Okay, so a free particle in one dimension. Okay.
Excuse me, sir.
Yes.
Sir, actually, I have a doubt when we are saying that there are k coordinates, right? So
Yes.
for each coordinate, like for q1, there will be some correct path. Let's say q01, right? So and for other coordinate, it will be different. Like
No. The path is one. The path is the just one path, and that is the path in the multidimensional plane. What I mean by that is that suppose you have just q1 and q2, so that I can draw this thing. Okay. So this is your say q1, and this is your q2, and this is your t. Let's say. Okay. Or rather, I can even uh, not even, so let me draw q3 here. Okay, and t is an implicit variable, is it? So what I mean is that at t equals t1, the thing was here, and at t equals t2, the thing is there. Okay, now you see that this is a path in itself, and this is defined by q1 equals q10t, q2 equals q20t, and q3 equals q30t simultaneously.
okay, so all the equations will be always be satisfied for this path, right?
Yes. So the in the multidimensional space, the equation of the path is basically the parametric equation. So for example, when you talk about, you remember this parabola, the parametric form of parabola, I think it is x equals 2at and y
Yes, sir.
equals at square, something like that. So you think like that. So this together defines the parabolic path.
Okay, sir. Now I understand.
Okay, so so in the multidimensional space, that's your path. The path is described by all these things simultaneously, and in this you are basically fiddling with the kth coordinate. Okay, that's it. All right, anything else?
No, sir, fine.
Okay, great. So now let us take the free particle in one dimension. So now we will use our intuition from Newton's law. So how does a free particle in one dimension behave? Okay, so it maintains constant velocity, right? It maintains constant velocity. Now, how would be its trajectory in the x space? So if I try to draw its trajectory in x space, let's say let's say this one. So this is my x, and this is my t, and let's say it has a velocity of v0, whatever that is, and at t equals t1, the particle was here. So this is my x1 t1, and at t equals t2 the particle would be, say, here. That is my x2 t2. Okay. Now if you know about Newton's first law, you know that this particle should be traveling to from x1 t1 to x2 t2 in absence of any force through a straight line. Okay. So you draw a straight line, and this is my correct path. Okay. So this should be my correct path in the xt space. Okay. It will not take anything else. It will not go via this one. Okay. This is also an alternative path it could take, but Newton told us that it will follow this one, because this if x1 t1 and x2 t2 are connected by a straight line, then this means uh, uh, propagation with a constant velocity. So this is my correct path. The orange one is my correct path. So in the xt plane, what is the system trying to do? It is trying to minimize the distance between this point and this point. Okay, because the correct part is the straight line, and we define straight line by the minimum distance between 2 points, right? So what it is minimizing, so that the distance that I write as ds is basically integration, sorry, any length element, let's say between 2 points, would be dx square plus dt square, right? And the total s would be the integration from t1 to t2 dx square plus dt square, the summation of all these things. And rather we may write 1 plus x dot square, like say dx dt, the x dot means dx, dx times dt. Okay. So basically you see this can be converted into a minimization problem. So the thing, so this is the same form of S equals L dt, but we can simplify things further. Okay, we can make our life even simpler. Okay, so the thing is that minimizing the distance itself and the square of the distance are the same thing. So this square root seems like a burden. So I mean, minimizing square root of 1 plus x dot square and minimizing 1 plus x dot square is the same. So if I write a minimization principle which I am trying to minimize, so I can take basically L equals 1 plus x dot square, and I can ask that I am trying to minimize S equals L dt, and that should give me this path, okay, from this abstract principle. So now from this, I realize that to describe the motion of a free particle in one dimension, I can alternatively formulate this as a minimization principle. The thing that I am trying to minimize is this. Okay, is given by this function, this Lagrangian function. Again, this one might be unnecessary because any constant added to the Lagrangian adds nothing. So so L is, you can say, is basically x dot square. Okay, L is proportional to x dot square, and so I would get equation of motion by that. Okay. Usually a constant is kept, so the constant, so that the dimension of L is matched. So I mean, if I try to minimize x dot square, then k times x dot square, where k is a positive constant, will also be minimized. Okay, so I can write down that, okay, L equals kx dot square might be a Lagrangian function for a free particle in one dimension. Now you can apply the Euler-Lagrange equation and find out the equation of motion is x double dot equals 0, which is fine because that is the equation of motion, and that is basically telling you that the acceleration is 0, that is, it is moving with the proper velocity. It's a constant velocity. right? So remember, I told you the Lagrangian is not unique. So by any means, if you could guess one Lagrangian, that is good enough, and without any loss of generality or without any loss of any information, you can proceed with that Lagrangian. It's no problem. Okay. And I could use this to guess the Lagrangian of a free particle. Now, if I apply my intuition, okay, remember I'm not proving anything. I'm just trying to give you a feeling how from this, how can I encode our known laws of physics in the Lagrangian formalism, and later I would give you a glimpse how these Lagrangians can be so-called guessed from a more general principle of symmetry. I have not uh, done that yet. So what I have, hello,
So there's a square root in 1 plus L whole square root. So L is this one square root.
no, what I said is that basically if you are minimizing this square root of this length, or like the square root of this and minimizing this are the same thing. Okay. If you still do not yeah, sorry, what?
Got it, sir, got it.
Okay, okay. And if you are still not unconvinced, I mean, if you apply this in the non-relativistic regime, you can expand this because x dot, the velocity is very small. So this should be approximated as 1 plus half x dot square. Okay. So you can do from that as well. Okay. And that's why I wrote L equals kx dot square. Now, remember my Newton's second law. So Newton's second law is, you can write it as mx double dot equals minus del v del x. Okay, that is the thing. Now, to connect this with Newton's second law. So Newton's second law is applicable when there is a force and there is no force. So when there is no force, I see that my del L del x dot is kind of 2k x dot, and d dt of del L del x dot is 2k x double dot. Okay. And my del L del x was 0 because uh, L did not depend on x at all. Okay. Now, if I try to connect this with Newton's second law, I see that a term like this 2k x double dot, is already present here. So I can guess that this mx double dot term will come from a term like this. And if I take k equals m by 2, so if I take k equals m by 2, this term fixes it. So I do not need to fiddle with this del L del x dot thing. The extra piece that comes here can be attributed here because this was 0 for a free particle, del L del x equals 0. But if I now associate this minus del v del x with del L del x, then I am done. I have guessed a valid Lagrangian for Newton's second law also. Okay. So what I would do, what I want is that del L del x would be equals minus del v del x. Okay. In other words, what I am suggesting here is that for Newton's second law kind of thing, the x dependent part of L, so that del L del x, the x dependent derivative of L, should purely come from V and nothing else. And the x dot dependence derivative of L should come from kx dot square. If I can do that, then I am done. Okay. So from these inspirations, I write L equals half mx dot square minus vx. And you see, both of these are satisfied. Okay, so del L del X dot, so del L del X dot comes from this, and del L del X come from the second term. So this contributes to del L del X dot, and this contribute to del L del X, and as a result you get Newton's second law. So again, these are all guesses, these are not proofs, because I told you, given an equation of motion, you cannot uniquely prove that that this Lagrangian is the correct one. In fact, there is a problem in a homework that uh, basically tells you better about these things. Okay, you can add to these many different things, and equation of motion will still be the same. So this is just one Lagrangian that I have guessed. Okay, and you see that this is applicable only uh, for forces that are conservative, where you can express the force as del v del x. Okay, otherwise you cannot apply this. So for kind of from this exercise, from the idea of this, you can say that for conservative system you can try with L equals t minus v, and that's why in most cases this L equals t minus v works, because you are given conservative system like harmonic oscillators or I don't know, things like that. Okay, Coulomb potential, things like that. Things are conservative system, but if you have seen problems with, say, damping, or whenever there are dissipative forces present, this prescription will not work, because you cannot express F as del v del x. Okay, so this L equals t minus v breaks down. You have to devise something else. So the lesson you learn is that there is no correct Lagrangian for a system. If you can somehow guess one Lagrangian, you are good enough to go. Okay, so there is no correct Lagrangian. Any Lagrangian is good enough. Okay, I will pause for a brief moment to take questions if anything is unclear. And yesterday there was a question, someone told me that how to connect this QT with physical things, like what does this QT means? Can I give an example? Now, if he is present here, can you tell me if things are clear to you now, that you understand what QT means? Because Q is analogous to X here, and T is analogous to time here. Okay.
Yes, sir.
Okay, good. So now let me proceed. So actually there is more to Lagrange's equation than just merely connecting with the Newton's second law. Okay. So I already told you that so these are my things. So del L del X dot, if you calculate, so this comes out to be your mx dot, which is basically the momentum in the x direction. Okay, and del L del X is minus del V del X, which is force in the x direction. Okay. So the Lagrange equation, this d dt of del L del X dot equals del L del X. If you use these analogies, then you can see that this is basically Newton's second law. Okay. This dpx dt equals force in the x direction, right? And actually, if you look at the structure of the general Lagrange equation, it tells you that d dt of del L del qk dot equals del L del qk. Now, just in the analogy with this one, like this del L del x dot being px, that I explicitly said. So if qk is my coordinate in the kth direction, let's say there exists certain direction which is the kth direction. And if I identify an analog of momentum, so I will identify this del L del QK. So this I call PK is the analog of momentum corresponding to QK. Okay, and this thing I would call my generalized momentum. Just like here comes in. So then the left hand side reads dpk dt. Okay, the rate of change of certain momentum. Then in a similar way, I identify my right hand side. What is the rate of change of momentum? Momentum is some kind of force. I mean, if I am inspired by Newton's second law, so this is some kind of a generalized force. So the whole Lagrange's equation, basically I embedded the whole Lagrange's equation in the simple form of Newton's second law. So the Lagrange's equation appears to be nothing new. It's just dp dt equals fk if you know how to look at it. Okay? It's just second law. It's second law of motion. And I would say in many ways it is more powerful than Newton's second law, because uh, it does not rely so much on the physical intuition. It tells you that if you can somehow guess the Lagrangian, then you know everything about the system. Let me give you an example which kind of illustrates these ideas. Okay. Hold on a minute. I have to take this call. I have a call here. Yes. So the example I want to give here is the point particle in 2 dimension. So let me say, so point particle in 2D polar coordinates. Okay. So you know it will have two components of velocity, the r component of velocity being r dot, okay, and the theta component of velocity being r times theta dot. Okay, and the potential energy would be in general a function of r and theta. For central force it is a function of r only, but in general it's a function of r and theta. So if it is a conservative system, by conservative system I mean that I am implicitly assuming that the force that is governing your system is obtainable from a scalar potential. Okay, so using the same spirit you write basically is L equals your t minus v. So t is basically half m r dot square plus r square theta dot square, okay, minus v of r theta. Okay, now there are two generalized coordinates here, two coordinates like r and theta. So the equation of motion corresponding to r, if you calculate, so equation of motion for r, so that would be given by d dt of del L del r dot equals del L del r. So you calculate that using those things, and you will find out to be that is equals m r dot minus r theta dot square equals minus del v del r. Okay. Good. So this is the radial equation. Now remember, if it is, so there are two components. One is the actual force. So if you draw a diagram like this, if something is rotating in this direction, then to bend its curve, you need a centripetal force, right? So bend it in this way, so that is so you need a centripetal force, and this centripetal force is, you remember, m omega square r. It is in this direction. Okay. Uh, so that's why you see, since it is in the minus r direction, so that's why you see the centripetal force is subtracted. So this m r double dot minus the centripetal force. Okay, that would be equals to your net force in r direction. Okay, so that is this, as you expect. And in the next, the more interesting part is equation of motion for theta. So equation of motion for theta. So that, if you calculate, would be d dt of del L del theta dot equals del L del theta. And you notice this. So this is m r square theta dot equals minus del v del theta. Now, how do you obtain that? So how do you interpret this thing? Okay. So remember that this force had two components. One had r component and another theta component. So the gradient of v, so f equals minus of gradient of v, and the gradient in the polar coordinate would be given by minus del v del r cap minus 1 by r del v del theta cap. Okay. So the first thing, this is your r component that I wrote as fr, and this is your theta component. That was that f theta. So that equation that you have here with this d dt of m r square theta dot actually reads so d dt of m r square theta dot equals minus del v del theta, if you notice, is r times f theta. Now r times f theta, what is that? Okay. So r times f theta, if you notice that what is r cross f, then r cross r would be 0, only the theta component remains, is precisely r into f theta. Okay. So this, this is your torque. So this guy on the right hand side is your torque. And you can perhaps see what is this. So this is your angular momentum, that are not a j. Okay. So you can check that this is your angular momentum is r cross p. So this is your angular momentum. So what you have here is just dj dt equals your torque. That is there. Okay. Now notice that how many things got suppressed here. So I did not talk about, I didn't draw a single figure. Okay. Even if I did not know about this particle motion in two-dimensional polar coordinates, I could still find out the mathematical truth behind it without knowing anything, as long as I can write down the Lagrangian correctly. So if I can guess the Lagrangian, I can get the correct equation of motion. Notice the role played here by these things. So when you talk about the equation of motion corresponding to theta, this theta is treated as a generalized coordinate. It's similar to qk. Okay, and this theta does not have the dimension of length. Usually you have the impression that the coordinates would have a dimension of length. If you have that, now it's time to get rid of that. Okay, so that's why this theta plays the role of a generalized coordinate, and the momentum corresponding to theta, which is del L del theta dot, is just the angular momentum, because theta is a coordinate associated with rotation, so how much you are rotating your system, and that's why uh, I- uh, so the momentum corresponding to the generalized coordinate theta is just the angular momentum. Now angular momentum has a different dimension than momentum, you know that. So this justifies my naming convention. So previously I defined this to be my generalized momentum. I see that it really makes sense if I know how to interpret my results, and if I see a generalized coordinate, I can define a generalized momentum and generalized force corresponding to that particular coordinate. Okay. There is more that you can extract from here on this simple exercise. So what happens if L does not explicitly depends on theta? So suppose L doesn't explicitly depend on theta. What I mean is that del L del theta equals 0. Now remember, where does the theta dependence of L comes from? It comes from V only. Only this part depends on theta, nothing else. So what I mean is that V doesn't depend on theta anymore. In other words, the common name that you know this and know it by is that the V is central. So V is a central potential and it does not depend on theta. And then you see that these terms are all 0 for a central potential, and what you have then is basically dj dt equals 0, or your angular momentum is conserved. Okay. This is the well-known result. You have done it in many different ways. So if your potential is a central potential, it does not have an angular dependence, then your angular momentum is conserved. How beautiful is that, and how neatly it comes into being. Okay. So there is a straight bit of generalization here. Okay. So remember, the master equation from which all these things transpired from is my definition that this dpk dt equals del L del qk. So this is my Euler-Lagrange equation. Okay. Now in general, if I say that L is independent of qk, that is what I mean is del L del qk equals 0. If this happens, then usually this qk is called a cyclic coordinate. Okay. And then what you have is dpk dt equals 0, that is pk equals constant. So what I mean is that if L is independent of qk, then the generalized momentum corresponding to this qk, which I call as pk, is conserved. Okay. So if a coordinate is cyclic, then the generalized momentum corresponding to that coordinate is a conserved momentum. Okay, and this is the statement, essentially the statement of something called the Noether's theorem. Okay. Now there are some subtle aspects of this statement. Okay, I have not proved it generally. Hopefully, I will do it later. Okay. But to give you the essence of what is happening here, notice in the one-dimensional case. So in the free particle case, I had L equals half mx dot square. No free particle, just a free particle, no force at all. So here I have del L del x equals 0, because L does not depend on x, and that's why I had the equation of motion to be dpx dt equals 0, that a linear momentum is conserved, and that's why it moves with a constant velocity. Okay. Now this means that if del L del x equals 0, if L does not depends on x, then that means if I change x by an additive constant, that means if I translate the origins, if I change x to x plus a, my Lagrangian does not change. So L does not change. Because if I shift my origin, still x dot equals x dot. So I do not do anything with x dot. So x dot does not change. X dot equals x dot. But I am shifting my origin. So I am translating. Okay. So that means that this Lagrangian has a translational symmetry. This Lagrangian doesn't tell me where to choose my origin. In other words, now pay particular attention to this. You need to be familiar with this language if you are to go further. In other words, if I have say simple harmonic potential, if half m omega square x square, by having this thing itself, I know that there is a preferred choice of origin. So by writing this, you are saying that your potential is 0 at x equals 0. So you have to choose your origin here. Okay. So your origin has a preferred location if you have this Lagrangian. But if you have just this Lagrangian, then your Lagrangian does not have a preferred choice of origin. You can choose your origin anywhere. And that is the essential statement of symmetry. So this Lagrangian, so in Newton's language, you would say why the linear momentum is conserved. In Newton's language, you would say because there is no force. But in Noether's language, you would say because there is a translational symmetry in the Lagrangian. Because if I change my coordinate from x to x plus a, my Lagrangian doesn't change, and due to that symmetry, my linear momentum is conserved. And again, if in the same token, if you have del L del theta equals 0, that means L does not contain theta. That means if you change to change theta from theta to theta plus another angle, so theta plus 45 degree, if you rotate your coordinates by 45 degree, your Lagrangian does not change. So your Lagrangian possesses a rotational symmetry. And because of that, the momentum that is associated with rotation, which is my angular momentum, is conserved. Okay. So these are the statements that are more general than the statements regarding force and so on and so forth. So if you are not used to this formalism, and if you are thinking about lessons from your past years, so why angular momentum are conserved and why say linear momentum is conserved are two seemingly different phenomena. In one case torque is 0 and another case force is 0. Okay. So that's why. But now you try to unify those things and you say that all the things that we see conserved, like any momentum that is conserved, that is because of a symmetry, of a certain symmetry, which in general I will dub it as translational symmetry. So in general, if del L del QK dot, if del L del QK equals 0, if del L del QK is equals 0, that means Lagrangian is invariant under the translation QK going to QK plus epsilon. So there is a translational symmetry in a general sense. There is a translational symmetry along the QK direction. And that's why the momentum corresponding to that coordinate is 0. Okay. So so this is the first step when you start thinking in terms of symmetry rather than of forces. Okay. And try to read a bit and try to get familiarized with these concepts. And perhaps yeah, my time is up, so I will stop here, and I can now take questions for a few minutes. Okay, so tell me if anything is unclear here. Yes.
Hello?
Yes, tell me.
Sir, actually, like in this case, we are saying that, sir, the previous case we have discussed is for potential, right? Where potential is defined for conservative force.
Yes.
So, in case of like where there is any number of non-conservative forces in the system, and if there is like conservation about a certain coordinate, let's say for momentum. So, how in that case we will explain that conservation through this Lagrangian thing?
I'm not sure if I understand everything completely. If there are non-conservative forces, first of all, actually, okay, I have to uh, uh, refine your concepts here. Let's say, so uh, when everything is taken care of in the grand scheme of things, there are no non-conservative forces. That's the misconception. So by non-conservative forces, you mean that the energy of one form is being translated into another form. Okay. Uh, so if you think about friction, friction is not a non-conservative force. The work you put in is not wasted. It's just transformed into heat energy. Okay. So if you take everything into account, your total energy is still conserved. So only problem with those kind of forces is that you do not have a potential formalism for those forces. Okay. So so how to write down potential for those things? The answer is you do not try to write down a potential for those things. Okay. There are other way to tackle this thing. Uh, one example will be in your electromagnetism that I will perhaps cover. In the case of electrostatics, you say del cross E equals 0. Okay, and since del cross E equals 0, you can express E as grad phi.
Mhm.
Okay, but in the case of electrodynamics, you see this changes to minus del B del T. Okay,
Yes.
it's not 0, but do you say electric field is non-conservative? Okay, so this basically means that the electric field energy is being transformed into magnetic field energy and vice versa. Okay, so nothing is non-conservative here. Okay, so basically your
It's
life. Sorry, what?
it means that that it is conservative, but like its potential cannot be defined, right?
Yes, I mean the you should not use the term conservative here. You just say the energy is conserved, but the fields cannot be expressed as simply as this. Okay,
Okay.
so you have to use a more complicated thing like I guess you have
Vector
seen this.
potential thing.
Yeah, something like this. Okay, and then things and this is not just a simple scalar potential. So there are ways to handle when we have energy is being converted from one sector into another sector. Okay, so that's why in as we move along, we do not think about potential anymore. In fact, in special theory of relativity, the concept of potential doesn't exist because the potential means action at a distance means, I mean, propagation of information at infinite speed. Let's not get into there. And that's why in electrodynamics probably you will be hearing something about called the retarded potential. But that's for later. Okay. So for now, let's say as long as we are dealing with conservative things, we can define a potential. Uh, in the case of non-conservative things where we cannot define a potential, we have other ways to guess the Lagrangian, and I will come to that. Okay. So
Okay,
we do
sir.
not try to do it by t minus v. We use some other things. Okay, because t minus v, you see the scope of application is very narrow. There are only a few systems that complies with t minus v. Okay.
Okay, sir.
Okay.
Yes.
So yeah, let's wait. Let's proceed further. And again, at the end, if you are not satisfied, you can ask me after 5 or 6 lectures. Also, not a problem.
Surely.
Okay. Okay. Anything else? No other questions? All right then. So I will now stop recording. and